Check out this empty box. Now, check out this lid that I can put on the empty box. Let's say there is no resistance, so that if I gave this lid a little nudge, it'd just keep moving with a constant speed. Let's say there's no air resistance, no resistive forces at all. Now, what I'm going to do, I'm going to stick a fluid, let's say water, and I'm going to fill it to the brim all the way to the top. This thing was overflowing. This goes all the way to the top. Now what happens is you take this lid, you go to slide it across again, you give it a little nudge, it doesn't keep going, it slows down and stops. You give it another nudge, it slows down and stops. The fact that this fluid's in here now is resisting the motion, that's because it's viscous. What do I mean by that? I mean that when this lid was moving across the top, the fact that this fluid was in contact with the lid caused this topmost layer to start moving with the same speed as the lid. There's adhesive forces between this fluid and the lid. On an atomic and molecular level, this fluid gets pulled with it. And so it resists the motion, but it's worse than that, because if this topmost layer gets pulled this way, then the layer right below it gets pulled by the topmost layer, and this secondmost layer pulls this thirdmost layer, and this keeps going down the line, and what you get is a velocity gradient, is the fancy name for it, which just means that this velocity of this fluid gets smaller and smaller. Once you get down to the bottom, well, now the fluid is in contact with this surface at the bottom, and this surface at the bottom is not moving. This fluid that's at the lowest most point doesn't move at all. All right, so that's why this lid slowed down when we gave it a nudge. It was dragging that fluid along with it. And if it exerts a force to the right on the fluid, then the fluid is going to exert a force by Newton's third law to the left on the lid, and I'm going to call this a viscous force. I'm going to call it FV. So what does this depend on? What does this viscous force depend on? One thing it depends on is the area, and not the whole area of the lid. It's just the area of the lid that's actually in contact with the fluid. So if you imagine the dimensions of this box would only expand here. So it's only that part of the lid that's actually in contact with the fluid. So that area, and it's proportional to that area. The bigger that area, the more fluid you're going to be dragging, the larger the viscous force. That makes sense. So it's this area here. And something else that it depends on is the speed with which you drag the lid. So the faster I pull the lid, well, the faster I'm going to be pulling this water. The bigger that force, which means the bigger the viscous force. So it's proportional to the speed as well. It's inversely proportional to the depth of the fluid. I'll call that D. And then it depends on one more thing. It depends on the viscosity of the fluid. Maybe the most important factor in this whole discussion. Eta is going to be called the viscosity of the fluid, or the coefficient of viscosity. And what this number tells you is how viscous, how thick, essentially, the fluid is, how much it resists flow. And so coefficient of viscosity, so to give you an idea, honey or corn syrup would have a large viscosity, water would have a smaller viscosity coefficient, and gases would have a coefficient of viscosity even less. So what are the units of this coefficient of viscosity? Well, if we were to solve for the eta, what would we get? We'd get force divided by area. So this would be force divided by area and multiplied by the distance divided by the speed. What units do these have? Force is in newtons, distance is in meters, area is in meters squared, speed is in meters per second. So I bring that second up top because it was divided in the denominator. So it goes up top. And what am I left with? Meters cancels meters. And I'm left with the units of viscosity as being newtons per meter squared times a second. But a newton per meter squared is a Pascal. So this is Pascal seconds. So these units are a little strange. But the units of eta, the coefficient of viscosity, is a pressure times a time, Pascal seconds. But some people use the unit poise, and 1 poise is equal to 1/10 of a Pascal second. Or in other words, 10 poise, and it's abbreviated capital P, is 1 Pascal second. And so you'll often hear this unit poise as a measure of viscosity. So what are some real life values for the viscosity? Well, the viscosity of water at 0 degrees Celsius is, and I'm not talking about ice, but water that's actually at 0 degrees but not frozen yet, is about 1.8, but 1.8 millipascal seconds. And another way to say that, look at millipascal seconds, that would be a centipause, CP. Because a pause is already 1/10 of a Pascal second. Remember, one pause is 1/10. And so a centipause is really a millipascal second. Or water at 20 degrees Celsius is 1.0 millipascal seconds, or centipause. Now you can see there's a huge dependency on temperature. The viscosity is highly dependent on temperature. The colder it gets, the more viscous a fluid typically gets, which you know because if you start your car and it's too cold outside, that car is not going to want to start. That oil inside is going to be more viscous than it's prepared for, and that engine might not start very easily. Blood typically has a viscosity between 3 to 4 millipascal seconds, or centipause. And then engine oil can have viscosities in the hundreds, around 200 centipause. And then gases would have viscosities that are even less. Air has a viscosity of around 0.018 centipause. Now it's important to note, if a fluid follows this rule for the viscous force and the coefficient of viscosity does not depend on the speed with which this fluid is flowing or with which you pull this lid over the top, does not depend on that, then we call this a Newtonian fluid. Then it's a Newtonian fluid. But if the coefficient of viscosity does depend on the speed with which the fluid is flowing or the speed with which you pull this lid, then it would be a non-Newtonian fluid. So if this coefficient of viscosity stays the same regardless of what the speed is, it's a Newtonian fluid. If that's not the case, it'd be a non-Newtonian fluid. Now, you might be thinking, well, this is kind of stupid. I mean, how many cases are we going to have where you're trying to pull a lid over a box? You've probably never tried to do that in real life, but this is just a handy way to determine the viscosity. Once you know the viscosity, you can apply this number. This is a constant of the fluid. Now, anywhere that this fluid is flowing, now that you've measured it carefully, you could determine what kind of flow rate you would get. So imagine, let's get rid of all this stuff here. Say you had a stationary tube or a pipe and there was a fluid flowing through it. Maybe it's a vein or a vessel and it's blood flowing through it. Anyways, now it's stationary though. Both the top and the bottom are stationary. So that means the fluid near the top and the fluid near the bottom aren't really moving, but it's the fluid in the middle that's moving fastest and then slightly less fast. And you get this somewhat parabolic type velocity gradient where it gets bigger and bigger and then it gets smaller and smaller. And so the velocity profile might look something like this. And if we wanted to know how much volume of fluid, how many meters cubed of fluid pass by a certain point per time, we can figure that out. There's a formula for this. The volume per time, the meters cubed per time. The formula is called Poiseuille's law. And it says this. It says the volume that will flow per time is dependent on delta P times pi times r to the fourth divided by 8 eta times L. Now this is a crazy equation. Let's break this thing down and see what it's really talking about. So here's Poiseuille's law. So this delta P is referring to the pressure differential. So there'll be pressure on this side. We'll call it P1. There'll be pressure on this side, P2. If those are the same, this fluid is not going to be flowing very long. There has to be a difference. If we want the fluid to flow to the right, P1 has to be bigger than P2, and the greater the difference, the greater this difference, P1 minus P2, the more volume that's going to flow per time, and that makes sense. And then pi is a geometric factor, r to the fourth. This r is referring to the radius of the tube, so that's r. And then 8, and eta we know. Eta is the viscosity. So this is the viscosity of the fluid. And the volume flow rate's inversely proportional to the viscosity, because the more viscous the fluid, the more it resists flowing and the less meters cubed you'll get per second. And it's inversely proportional also to the length of the tube. The more tube this fluid's got to flow through, the smaller the volume flow rate. So this is called Poiseuille's law. It's useful in a lot of medical and engineering applications. For whenever you want to determine the volume flow rate, now you've got to be careful. We're assuming this is a Newtonian fluid. That means eta is not a function of the speed of the fluid. We're also assuming you have nice streamlined laminar flow. So laminar flow means these layers of fluid stay in their lane, basically. They do not cross over. Once you start getting this, you'll start getting turbulence, and once you get turbulence, you'll need a much more complicated equation to describe the dynamics of this. So we're assuming no turbulence and a nice Newtonian fluid, and if that's the case, Poiseuille's law gives you the volume that flows through a pipe per time.